Hi, in this video I want to talk about the type of geological resources that are formed by chemical precipitation processes. There's a collection of industrial minerals and even ore minerals that are created in this way, and it's important that we understand actually how these things are formed, because that's going to inform where we can find them. There are several sedimentary processes which can concentrate geological resources, including ores, in particular places. For example, we have residual deposits where other material gets washed or leached out of a rock, leaving behind the elements that we're interested in. Bauxite, for example, is formed this way where aluminium gets left behind. We also have placer deposits where transport and erosion processes sort out and concentrate particular geological resources. Both of those we'll deal with in other lessons. I want us to focus on the minerals that are deposited as a chemical precipitate. And that could be in the sea, for example, a banded ironstone formation, or it could be an evaporite deposit. Now, we've already discussed those, but I want to revisit those ideas. Let's start by looking at a banded ironstone formation. These are very, very important iron resources. They create very extensive and very, very high grade iron deposits. But we only find these in Precambrian rocks. They're very ancient. And the reason for that is the way in which the Earth's atmosphere has evolved over time. Back in the Precambrian, there was very little oxygen in the environment. So when mafic minerals chemically weathered and released iron, that iron didn't oxidize. It stayed in solution. Now that meant the iron could be transported to the sea by rivers, and it was only in the sea where we had some early photosynthesis occurring that this iron would change from a soluble ferrous iron to insoluble ferrous iron oxide, and therefore it be deposited on the seabed. So it'd be precipitated in the sea and deposited in layers on the seabed. This doesn't happen today. There's too much oxygen in our environment now. So these are confined to these ancient deposits. We tend to see these things without a great deal of clastic sedimentation. It does suggest that chemical precipitation was the dominant process in this. There can as well have been some secondary enrichment of this, increasing the grade of iron, with many of these deposits being over 60% iron. Often this mineral is hematite. Can also be some other iron minerals in there, for example, goethite. Now, banded ironstone formations are, because of the nature of how they form, confined to these ancient areas of continental crust, the continental shield or cratons. You can see on this map how these main banded iron formations in North America, South America, Africa, and Australia, also in Asia, really spread across the world, are almost entirely found in these ancient fragments of continental crust. The processes for these are still really being worked out. Remember, we can't really use uniformitarianism to explain this. If we look at one of these deposits, this is the Hamersley range in Western Australia, we can see these are located in really quite remote areas. Generally, infrastructure has to be built to develop mines in these areas. But the sheer quantity of the resource, in this case, total reserves of 13.5 gigatons, and hypothetical resources of perhaps the same again, okay, of very rich ore, okay, is worth the investment. Some of the mines that result are enormous. Mount Tom Price, one of the mines, 10 square kilometres of mine with maybe 900 megatons of ore, with 64% of that ore being iron. It's an incredibly rich resource. You can see from the photograph here that they make from very obvious resources. Exploring for these isn't particularly difficult. Banded iron formations are deposited very much in the sea. Evaporites, though, can be formed in either very shallow seas, where you have an almost entirely separate lagoon within the sea, or possibly in a playa lake deposit. Where we have an input of salty water, so that could be surface runoff in a desert, or could be seawater that's able to only at certain times get into a lagoon. With a lot of evaporation, very quickly that water will become oversaturated with the dissolved minerals. When that happens, we'll get precipitation of those minerals at the bottom of the lagoon or the lake. We have got to remove a lot of seawater. Okay? For example, 3 meters deep of seawater, if you evaporate it off, will produce 5 centimeters of evaporite. So if you need to have lots of continuous supply to build up economic quantities of evaporite deposits. As we learn when we're looking at these as just as sedimentary rocks, there is a sequence of deposition. Calcite is the least soluble, is the earliest to be deposited, followed by gypsum, halite, and finally things like potassium salts, where virtually all the water has to be evaporated. The two most important of these deposits are gypsum. In the UK, we find significant deposits of this up in the northeast of England, or halite, rock salt, where we can find very large quantities that have been deposited in Northern Ireland and also in Cheshire. We use these materials for a lot of different purposes, beyond the obvious ones of plaster for gypsum and for putting on your chips with halite. Both of these types of deposits are important. We get resources from them, really we can't get easily in other ways. The future of evaporite deposits, I think, is even more important. They could well be a very, very important source of lithium, an element that, if technology continues to develop as it is, is going to become even more essential than is currently the case. Anyway, remember to come up with your interesting question and bring it along to class. I'll see you then.